Maximum difference item scaling. Researchers are commonly asked to measure respondents' reactions to multiple items or levels, such as brands, product service features, advertisements, political candidates and positions, and psychographic profiling statements. However, there are a number of problems with rating scales. First, there is a lack of discrimination among items. Respondents use the scale in a limited way, registering many ties. Increasing the number of scale points doesn't solve the problem. Second, depending on the respondent's culture, age, or educational background, they may not be able to understand how to use the scale properly. Third, there is often scale use bias. You'll find yay-sayers and naysayers, which is an intercept issue, wide scale versus narrow scale raters, which is a variance issue, and scale use often varies across countries. Fourth, standardizing the data with a mean of 0 and a standard deviation of 1 can remove these differences, but these steps are often not taken in practice. After standardization, data are less intuitive to managers. Here are some possible solutions. First, you could do some ranking questions, but these become impractical with lots of items. Second, you can use constant sum allocation. However, this also becomes impractical with too many items. Respondents may not allocate the chips independently, and making the answers to sum to a particular value may be distracting. Or third, you could use a Q-sort, which is a special rating scale, where you force respondents to use each scale point a specified number of times, typically following the normal distribution. This is probably better than standard ratings and may be nearly as good as MaxDiff. The method of paired comparisons simply displays a binary comparison, and you simply choose which one you prefer or desire. This is repeated for a number of comparisons. It is a very old technique, but a very good technique. For example, let's suppose you were defining some attributes for a restaurant. One of your questions could ask, which is more important to you in a restaurant? A clean eating area, or that the food tastes wonderful? Consider 3 items, A, B, and C. There are 3 possible comparisons if we assume A and B and A, etc. are equivalent. In other words, A versus B and A versus C and B versus C. Generally, with T items, there are 1/2 T times T minus 1 possible comparisons. For example, with 20 items, there are 1/2 times 20 times 20 minus 1, which equals 190 possible comparisons. Now, does each respondent have to evaluate all possible combinations? Well, if we are willing to make some assumptions, and particularly if we use some advanced techniques such as HB and latent class, then the answer is no. In 2 methodological studies, we found that asking 1.5T paired comparisons can yield useful individual level estimates using HB estimation. 1.5T comparisons can be designed using a cyclical plan. This diagram represents the following 9 comparisons. We got A to B, B to C, C to D, D to E, E to F, F to A to D, B to E, and C to F. Now, this would be a poor design, lacking connectivity. Items in the first set are not connected to items in the second. As a result, one cannot scale the items with respect to one another. The beauty of paired comparisons is that we can obtain interval-scaled measurements of items on a common scale using a series of simple paired comparisons, given many repeated measures of the same item within a respondent and especially across respondents. We derive the scores by observing trade-offs rather than asking respondents to declare the scores, as we do in conjoint analysis. Forced trade-offs lead to greater discrimination, and discrimination leads to more information. and it is simple. Even a small child could understand the task. Jordan Louviere introduced a new method called maximum difference scaling, also known as best-worst scaling, in the early 1990s. The method applies nicely to general scaling problems for multiple items. It can be thought of as an extension of paired comparisons. Here is a sample maximum difference best-worst task. Consider making a best and worst indication among 4 items, A, B, C, and D, where A is the best and D is the worst. We then know that A is greater than B, and B is greater than D, and A is greater than C, and C is greater than D, and A is greater than D. From only 2 clicks, we learn about 5 of the 6 possible paired comparisons. The only thing we don't know is the relationship of B to C. According to researcher Stephen Cohen, relative to rating scales, paired comparisons and best-worst item scaling are free from scale use bias, and they force trade-off of items, are better for audiences that might not understand how to use a rating scale well, and provide better discrimination among items and between groups of the items. MaxDiff is similar in many ways to conjoint analysis, which also forces trade-offs. Rather than asking respondents to directly score the items, we observe these trade-offs and derive the scores. The derived scores have interval-scale qualities. Scores can be derived at the individual or group level. Some people have said that MaxDiff is like a one-attribute CBC with many levels. But MaxDiff can be more generally applied to many research situations in marketing, economics, or sociology. There are 3 steps to designing an effective MaxDiff experiment. First, you need to develop your attribute list. Second, you need to decide the number of items per set, the number of sets per respondent, and the number of versions of the questionnaire that you want respondents to see. Third, you need to use experimental design software to generate a design featuring frequency balance, orthogonality, positional balance, and connectivity. Here is an example of 10 attributes that a fast food restaurant could use in a survey. We have clean eating areas with floors, tables, and chairs, clean bathrooms, whether or not it has health food items on the menu. We also have 2 attributes that measure different quantities of the same thing. So we have a typical wait time of about 5 minutes in line and a typical wait time of about 15 minutes in line. Next, we have reasonable prices. Your order is always completed correctly. There's a play area for children. The food tastes wonderful, and the restaurant gives generously to charities. Well, this is not a bad list. So, should there be any prohibitions? Probably. Items 4 and 5 deal with the same feature, but different time frames. We probably wouldn't want both of these items to appear in the same set of questions, because most people will almost always choose the shorter wait time. To investigate the number of items per set, a simulation study performed by Brian Orm in 2005 led him to make the following recommendations. First, only use 4 or 5 items per set. Second, there is little gain by showing greater than 5 items per set in studies of 10 to 30 items. And third, showing more than half the number of items under study per set can damage efficiency. Later research by Shun and Patterson with real respondents confirmed that 4 to 5 items per set is probably better than more. Therefore, it seems that showing 4 or 5 items per set in this case should work wonderfully well. Now, as far as the number of sets per respondent goes, in Orm's study, he suggests that you should display each item 3 or more times per respondent for relatively stable parameters at the individual level under HB estimation. If we show 10 sets to respondents at 4 items per set, each item of our 10 in the study will be shown 4 times. A single design, showing each item 4 times, can be nearly optimal in terms of statistical efficiency. Additional designs can further control for order and context biases and slightly improve efficiency. With computerized interviewing, we might as well include many versions. For paper and pencil implementation, perhaps 3 or 4 versions strikes a good balance between reducing context effects and manageability. You know you have a really good design when the following qualities are present. First, you have frequency balance, which means that each item appears an equal number of times. Second, you have orthogonality, when each item appears an equal number of times with every other item. We also call this independence. Third, you have positional balance, when each item appears an equal number of times in the first position, second position, third position, etc., in the set. And fourth, you have connectivity, when items are connected to all other items for each respondent via a chain of inequalities. However, please keep in mind that a design can be quite acceptable in practice that isn't perfect in all aspects. There are 4 different methods commonly used to analyze MaxDiff data. First, you have counting analysis, which you can do either separately for bests and worsts or combined. Second, you have aggregate logit analysis. You have latent class for multiple group solutions. And you have hierarchical Bayes, or HB. MaxDiff scores can be put on a scale that runs from 0 to 100 and the scores sum to 100, which makes it just as easy to work with as regular ratings data. It also provides excellent input to cluster analysis routines for market segmentation or turf for portfolio optimization. A weakness inherent in MaxDiff is that the scores are relative to one another. We never ask respondents if they like or dislike the items in an absolute sense. Depending on your goals, this may or may not be a hindrance. An extension to MaxDiff called Anchored MaxDiff resolves this problem, but not without reintroducing the scale use bias problem. This concludes the presentation on MaxDiff. Thank you for watching. For more information, please visit sawtoothsoftware.com.